We all know the mosquito as a universally despised pest, but out of sight, that exact tiny insect is solving one of our toughest engineering problems. Its anatomy is a highly evolved micromanufacturing tool. Understanding the mechanics of how it bites provides the template for building hardware at the microscopic scale. To understand why, we have to look at medical 3D printing. Researchers want to print complex biological tissues, and to do that, they use thick, syrupy materials called bioinks. Here is the massive physics bottleneck. When traditional nozzles try to push this viscous bioink through microscopic channels, they clog instantly. Building a nozzle that is microscopically precise while also resisting those dams costs an absolute fortune. The entire bioprinting industry has been stuck, desperately waiting for a microscopic tool that somehow defies standard fluid dynamics. Scientists in Canada realized that evolution already engineered a way past this wall millions of years ago. This diagram shows the cross-section of a mosquito's proboscis. It has specialized internal pathways built specifically to pump viscous, sticky fluids like blood. Those pathways prevent coagulation at a microscopic scale. The thick fluid flows continuously under perfect pressure, never sticking to the walls. The insect naturally perfected the exact mechanical requirements that human engineers have spent millions of dollars trying to invent. Rather than attempting to build a replica of this structure, the researchers integrated the actual mouthpart into their hardware to create a functioning biohybrid nozzle. Now, when they run their thick bioink through this organic tip, it flows flawlessly to build highly complex structures. Comparing precision, the biohybrid nozzle is exactly twice as precise as standard industrial ones. Tracking clog frequency, industrial hardware constantly fails, while the biohybrid flatlines at 0. It never jams. And this hyper-accurate tool costs just 60 rupees, under $1. By utilizing a biological component, the researchers wiped out the barriers of extreme cost, low precision, and constant failure all at once. Using organic structures directly in machinery represents a change in how we approach hardware manufacturing. Engineers can bypass years of expensive trial and error in the lab by borrowing parts directly from biology. While industrial-scale production of biohybrid parts remains a future challenge, this success proves that the primary mechanical barrier to affordable bioprinting has been solved. Researchers can now layer cells with enough microscopic detail to actually engineer functioning human tissues and complex organs. We spend immense amounts of time and money trying to invent our way out of complex problems using sterile rooms and supercomputers. Sometimes, the most advanced engineering on Earth has been flying around outside the entire time.